All right, let's jump right into this explainer and uncover the thrilling, absolutely true planetary biography of Mars. For centuries, we've looked up at that little red dot in the sky and just projected our wildest imaginations onto it. But today, we're going to peel back all those layers of myth to reveal a geological reality that is honestly far more mind-blowing than fiction.
To really understand our deep connection to Mars, we kind of have to look at humanity's long-standing cultural obsession with it first. There's this incredibly fun poem by P. Smith from the University of Arizona, written for the Mars Pathfinder mission back in 1997, and it perfectly captures why we keep going back. As he put it, we're looking for the mystery of life's early history. This enduring fascination is basically the perfect springboard into our planetary detective story today.
But long before we were sending rovers, ancient civilizations were already projecting intense meaning onto Mars. Our cultural fascination with the planet as this fiery, warlike deity, like the Babylonian god of fire Nergal or the Roman god of war, it stems directly from its striking reddish appearance in the night sky. And as we know now, that color is essentially planetary rust. It's just caused by iron oxide on its surface. Actually, the symbol we still use for Mars today, it literally represents the shield and spear of the Roman god Mars.
By the late 19th century, this fascination completely exploded into full-blown Mars fever. Astronomer Percival Lowell popularized this wild idea of a dying world populated by intelligent Martians who were frantically building complex irrigation canals just to survive. So the crucial point here is that Lowell wasn't entirely wrong about there being drawing channels on the surface. He was just off by a few billion years and completely mistook the natural scars of ancient catastrophic megafloods for alien engineering.
Okay, let's move into Section 1, Earth's ancient twin. We're talking about a thriving, dynamic planet.
Let's see how this builds our understanding of just how remarkably similar early Mars actually was to our own home planet. Notice the stark, really dramatic contrast between the low-lying northern plains and the elevated, heavily cratered southern highlands. In geology, we call this bimodal hypsometry, but we can translate that dense term into a clear crustal dichotomy. This massive split in the planet's terrain acts as a smoking gun, pointing us directly toward the existence of ancient oceans that likely filled that entire northern basin.
And this brings us to a really fascinating model called the GeoMars theory, which stands for geological evolution of Mars and related syntheses. In its first few 100 million years, Mars was incredibly Earth-like. It had a thickened continental crust formed by early plate tectonics. It had an aggressively active core dynamo generating a strong magnetic field that shielded the planet from the solar wind. It even had transient seas, massive lakes like Oceanus Borealis, and active hydrology with Earth-like precipitation, meaning it literally both rained and snowed on ancient Mars.
Which brings us to Section 2, the planetary engine dies. What actually caused Mars to die? If Mars was truly this thriving, dynamic twin to Earth, we're forced to ask a pretty tragic question. What caused it to stop? When you compare the internal structures and the thermal evolutionary paths of Mars and Earth, the harsh reality of Mars' smaller size becomes super clear. Because Mars is significantly smaller, it simply lost its internal heat much, much faster than Earth. This rapid heat loss pushed Mars right off the path of dynamic plate tectonics and forced it into what geologists call a stagnant lid regime, where the crust just entirely locks in place.
This is what we can call the tragedy of size. As those early subducting tectonic plates pushed cold material down deep into the mantle, they rapidly cooled the planet's core. And because of this, the internal dynamo completely died out prior to a period known as the Late Heavy Bombardment, which happened around 4 billion years ago.
Let's walk through the mechanics of that cooling core, because it's absolutely crucial. In its earliest days, the core is liquid. Then, plate tectonics cause what's called spot cooling, which births a solid inner core that drives convection. That's our active dynamo and magnetic shield. But eventually, the inner core grows so large that it freezes completely solid. Convection stops, the dynamo dies, and without that magnetic field, the planet's atmosphere was left entirely defenseless against the stripping power of the solar wind.
All right, Section 3, superplumes and floods. This is where we get into the catastrophic events.
So, plate tectonics shut down, and the magnetic shield fell. Let's look at the immense geological events that follow the death of that planetary engine. As plate tectonics ended, the final stages of subduction trapped massive amounts of water, carbonates, and sulfates deep down in the mantle. Over time, residual heat from the frozen core caused this volatile-rich material to melt and rise. This created what is known as the Tharsis superplume, an immense, persistent upwelling of magma that would violently, and I mean violently, disrupt the planet's surface for billions of years. This disruption is captured by a theory with a fantastic academic acronym, MEGA outflow. It stands for Mars Episodic Glacial Atmospheric Oceanic Upwelling by Thermotectonic Outbursts. Quite a mouthful, right? To translate that into plain English, it describes a cycle where Mars experiences extremely long periods of frozen, dry stability, which are then violently interrupted by relatively short episodes of magma-driven megafloods. Around 3.4 billion years ago, these thermal outbursts unleashed massive amounts of trapped underground water, temporarily reforming vast oceans on the northern plains.
To help visualize these Martian megafloods, the research paper pulls this brilliant analogy from none other than Leonardo da Vinci. Da Vinci once theorized an internal water cycle on Earth where subsurface pressures forced water upward, much as blood is pumped through the human body. While he was actually mostly wrong about Earth, his analogy perfectly describes the reality of Mars. These megafloods were literally like a planetary heartbeat, violently pumping trapped water out onto the dry surface.
And finally, Section 4. Where is the water? The ultimate planetary mystery.
So the big question is, if Mars had all this water, where on Earth, or rather, where on Mars, did it go? Well, look at the proof that it was there in the first place. Check out this distributary complex of alluvial channels in the Eberswald crater. Notice those intricate meandering curves? That is Earth-like paleomeander topography. It proves beyond a shadow of a doubt that persistent, laterally accreting rivers very similar to our own Mississippi River, once flowed right across this now bone-dry surface, depositing sand and gravel as they went.
So here is the crazy narrative twist. The water didn't just slowly vanish into the vacuum of space. Because the planet was so incredibly cold, that massive inventory of floodwater rapidly retreated back underground. Today, it is sequestered right beneath the surface in something called the cryolithosphere. This is a massive zone of ice-rich permafrost that spans 1 to 2 kilometers thick at the equator, and get this, up to 6 kilometers thick at the poles. The water is still there, it's just hiding in the dark.
Which leaves us with a truly thrilling thought as we watch modern rovers like Perseverance mark new milestones on the red planet. If oceans of water are still locked in the Martian permafrost right now, just waiting for the next thermotectonic outburst, what hidden signatures of ancient microbial life might be frozen down there with it? It's a profound mystery for sure, and one that absolutely ensures our cultural obsession with Mars is really just getting started. Thanks so much for exploring this amazing geological history with me.